In the world of electronics, a number on a screen is only as good as the tool that put it there. Today, we're going to go on a quest for the true value. We'll dive into how we can calibrate our instruments to get them perfectly accurate, and then we'll have to face down the invisible enemy that tries to corrupt every single measurement we take: electrical noise.
So here's our game plan. First, we'll cover the basic idea of calibration. Then, we'll uncover a really critical flaw in our basic measurement tools. After that, I'll introduce you to the amazing device that solves it, the potentiometer. And finally, we'll tackle that relentless problem of electrical noise.
All right, let's dive right in. What does calibration actually mean? I mean, when your multimeter tells you something is 5 volts, how do you really know it's 5 volts?
When you boil it all down, calibration is really just a simple comparison. You take the instrument you're using and you check it against a gold standard, a tool that you know for a fact is dead-on accurate. It's all about finding the truth.
A great way to picture this is like an old-school balancing scale. On one side, you have the reading from your instrument. On the other, you have the value from the trusted standard. The whole point is to see how they balance out so we can find that true, precise value.
Okay, so that's the theory. But how does this actually work in a real circuit? Let's take a look at the most basic calibration setups, because once we do, you'll see there's a sneaky little problem that affects almost every simple measurement you can make.
For a voltmeter, it's pretty simple. You just connect the standard meter right alongside it in parallel. For an ammeter, you put it in the same path, or what we call in series. I mean, these are super simple circuits, right? They almost seem a little too simple.
So we've got our tests all hooked up. We're getting readings. But this is where a huge question pops up. Is the very act of connecting our standard instrument changing the circuit? There's a hidden problem lurking in here that can totally throw off our results.
And here it is. It's called the loading problem. See, in order to measure voltage, even the best, most expensive instrument in the world has to sip just a tiny bit of current. But by taking that current, it actually changes the circuit it's measuring. It's this fundamental paradox. The act of observing something can actually alter.
So what are we supposed to do? How can we possibly get a true reading? Well, what if we could measure voltage without drawing any current at all? I know, it sounds impossible, but there's an incredibly clever tool designed to do exactly that: the potentiometer. This is the classic slide-wire potentiometer, and its genius is really in its parts. It uses a super stable voltage source, we call it a standard cell, and an extremely sensitive current detector called a galvanometer. Its whole job is to find a perfect balance point where absolutely zero current is flowing.
Now, before we can measure anything, we have to standardize the device. Basically, we have to zero it out. First, we connect our known standard voltage. Then, we physically set the slider on the wire to match that voltage. And finally, we adjust the circuit's current until that galvanometer reads exactly 0. We're setting our baseline for a perfect measurement.
This is where that balancing act really comes into play. We are literally balancing the circuit's voltage against the trusted voltage from our standard cell. And when that galvanometer needle hits dead center on 0, we know we've found the null point, a state of perfect balance.
Okay, once the potentiometer is standardized, we're ready to rock. We flip a switch, which connects our unknown voltage. Now here's the cool part. Instead of adjusting the current, we start moving the sliding contact back and forth along the wire. We're hunting for that null point again, and the exact spot where we find it tells us the precise voltage.
So that big slide wire is fantastic for understanding the principle, but let's be honest, it's not very practical. So let's see how this incredible no-balance method gets used in modern lab equipment to calibrate an actual voltmeter.
In any modern lab, you're not going to see a 200-centimeter wire. Instead, you'll see a box with a bunch of precision dials. The main dial makes the big adjustments, and a smaller dial lets you do the fine-tuning. It's the exact same principle, just engineered to be compact and incredibly precise. And here is where we get the payoff. We hook up the voltmeter we want to calibrate, and it gives us a reading, let's say 11.95 volts. But we know better, right? We know that reading has been tainted by that loading error we talked about earlier.
But then we bring in the potentiometer. We adjust the dials, we hunt for that zero current null state, and it reveals the true voltage completely free from any loading error, exactly 12.00 volts. That right there is the power of this method.
And this brings us to the final goal. We don't just test one voltage. We check a bunch of points all across the meter's scale, and we plot the errors we find. What this gives us is a calibration curve. It's like a unique correction map just for that one specific instrument.
So, we did it. We beat the loading problem. We have a perfectly calibrated instrument, and we can get the true voltage. But just when we think we finally achieved absolute precision, a new and much more insidious enemy shows up: electrical noise.
So, what is noise, anyway? Well, put simply, it's any unwanted electrical energy that just kind of piggybacks onto your signal. Think of it like electrical garbage that gets mixed in with the pure information you're actually trying to measure, and it corrupts everything.
The basic math here is really simple. You start with a nice clean signal. Then the universe comes along and adds a bunch of random noise. What you get in the end is a degraded, messy signal, where the original information is way harder to see.
Now, it's super important to know that noise really comes in two main flavors. Uncorrelated noise is like the constant background hiss of the universe. It's just always there. But correlated noise is way sneakier. It's a distortion that is only created when your signal is actually passing through the system.
And this enemy has a lot of different forms. It can be external, coming from things like radio stations, lightning, even other equipment nearby. Or it can be internal, generated by the random movement of electrons inside your very own components. It's everywhere. And that brings us to the final, really fascinating challenge. We've just learned how to find the true signal, but correlated noise is a distortion that's literally born from the signal itself. When the signal is off, the noise just vanishes. So the real question becomes, how do you fight an enemy that's a byproduct of the very thing you're trying to protect?